So up until this point, we have talked mostly about derivatives and tangent line problems. And today we're going to get introduced to the next second half, the big idea in calculus, which is approximating area under a curve. Now the area under the curve can represent a lot of other things, which we'll get to in a little bit. But for a little while here, we're going to just talk about it as the area underneath the curve. So this is the shaded, right? I'm just looking, for instance, here I have the shaded. This is the graph F. And the area between under a curve is essentially the area that's trapped between the curve and the x-axis, okay? So that is what I'm looking at here. Now I have the area shaded from 0 to 6 on the number line. I can alter that, I could make it a little bit bigger here, right? I could take it back here somewhere, but for this first example, for our introduction here, we're just going to look at the area under this curve between 0 and 6. Now the function is irrelevant. Okay, we're just thinking, okay, well, how am I going to go about figuring out what this area is, right? Because it's a curve. If I had, for instance, this triangle, right? This is another function, f, right? It's this line right here, and when it intersects, if I look at the area between x equals -2 and x equals +1 here, then it ends up being a triangle. And I can find the area of a triangle. That's just 1/2 times base times height. And here I have a base that's 3 units long, a height that's also 3 units long. So 3 times 3 is 9, times 1/2 is 9/2. So that's not even an approximation, that's an exact answer, right? So, but what happens if we have a curve, okay? So what we do is we partition it. Basically that means we're going to break it up into intervals and try to calculate areas of these into these other smaller sections of it and then add it all together. So that's kind of why we needed to learn about the sigma notation first, because we're going to add a bunch of stuff together. All right, so when we partition it, now we're mostly going to look at what we call a regular partition, and that just means that we're going to have uniform things. So I'm going to draw rectangles in here, and I'm going to draw essentially rectangles that have the same width. So there are other partitions where you don't have to use, what we're going to primarily look at is regular partitions where all of the widths of things will be the same, but they don't have to be the same, okay? So we're going to first look at, okay, so we're going to first break this into 2 rectangles, okay? So let me add some things to our picture here. So we're going to use 2 rectangles here, and this particular picture that I'm drawing, okay, this is called L2. Now we call it L sub 2. It's like kind of a little subscript 2 because it is, actually here is now I couldn't make Desmos in its labeling thing do the sub 2, but the 2 should be sort of like down here as a subscript. This is an L2 estimation, and the reason it's L2 is because, one, I have 2 rectangles, so that's the 2. And L means I'm going to use the left hand side of my rectangle as my height. So basically that means so here's my 2 rectangles, right? And I figure out the width of them by doing essentially, this is kind of my B over here. The 6 is biggest, and my A is my left-hand endpoint. So we figure out the width. Now it's not that hard to figure out that if I divide 6 into 2 pieces, it's 3 units long. But for more complicated ones, essentially we do B minus A, which would be 6 minus 0, over N, which is the 2 here. So our width of each rectangle is 3 units. And then we use the left-hand place as our height. So essentially what I do is I go to the place, okay, so this is my left-hand side of this first rectangle here. I run my line up until I hit my function, right? So that's at 4. And I'm going to basically draw this straight line across, right? So then my next rectangle is this one here. Here's the beginning, the left-hand side of my rectangle. I run it up to where it hits F at 4.9, and then I'm going to run it across. Now you can see this isn't a very good approximation, right? Because I'm missing almost like whole triangles up here. So this is what we're going to call a lower sum. So we can also do right endpoints, which we're going to do next. And basically a lower sum means that this is the lesser sum. So if I did right endpoints, which I'm going to do here in a minute, I'm going to have an upper sum. So somewhere between one that's bigger than this and this one is the actual area. So since this is smaller than the actual area, we call this the lower sum. So now let's put some numbers on our lower sum here. All right, so let's see. So we have this here. Actually, let's put the label on here. So this one here, right? So it's got a width, this area is 3 times f of 0 here. And f of 0, we saw when we click on this, is 4. So if we weren't just looking at the picture and we just had the function, we would plug in the left endpoint and that would be my height. So now I have width times height, which is 12. So this one is 12 square units. And then if I look at the other one here, I have, this one is 3 times the height at f of 3, which is 4.9, right? So we'll label that. And so basically, my estimation for this, oops, sorry, I didn't want to put that on there. So here's my estimation would be, essentially my total area then is 12 plus 14.7. So that was my estimation. Now I know that that's a really low estimation because I have these big gaps here. So let's try another estimation. Okay, so we'll use right endpoints in this next one. So that one we call an R2 estimation. So that just means we're going to have two rectangles using the right-hand side as the height. So drawing that in, let's see. So I have the same, my triangle, or I have the same essentially where it's broken up into, but my rectangles this time will look like this, right? So now I have an overestimation, right? So where the other one I had a big gap between basically here and here, right? And then here and here across this line, now I have a way overestimate. Now the actual area is somewhere essentially between my lower bound, which I found in the last one, which is 26.7, and my upper, right? My upper sum, which would be this one. So let's approximate this one here, right? So this rectangle will be 3 times, this time we're using the right hand endpoint. So f of 3 is 4.9. And let's see, we also have this one here, which is f of 6, 3 times f of 6, because that's my right hand endpoint. So that would be 7.6. And so when we do 3 times 7.6, we get this, making our total area that we're estimating at 37.5 square units. Now, the actual area is somewhere between 26.7, which was definitely an under, and 37.5, which was definitely an upper. So that's not super accurate. But what if I increase the number of rectangles I have? So let's do an R3, okay? So this time the width of my partition, right? The width of each rectangle, if I want 3 rectangles, that would be 6 minus 0, b minus a, over the number. So that means I'd have 6 divided by 3. So this time, the width of each rectangle will only be 2 units wide. So let me draw in my rectangles here. And again, we're using left endpoints. So there's my shading. And there's my next rectangle, and it's shading, my next rectangle, and it's shading. Now, definitely going to be an underestimate again, but I'm hoping that this one will be a little bit better than our last L2, right? So let's say we have, this one's going to be 2 times f of 0, which f of 0 here is 4, right? All I have to do is click on it. If I have f, then I plug in 0 into my function, right? And let's see, so then my next one would be 2 times f of 2. That's this, right? That's my height for this rectangle. So that's 2 times 4.4, which gives me 8.8. And then I have one more here, my biggest one, which would be 2 times f of 4. f of 4 is 5.6. When I multiply that by 2, I get 11.2. And so then I end up with my total area being 28. Okay, so for this one, it was 26.7, so 28 is probably more accurate, right? Because this one was definitely a way underestimate, so, or the the first one was a way underestimate. So this one is a little bit better, and it's in between the two that we first found. So you can kind of see maybe that I'm going to get more and more accurate as I go. Now, I want to bring this into the picture here. Okay, so first of all, my delta x, which is the width of my rectangle, is b minus a over n. So that is the big number, 6, minus the smaller end, a, because we're only, or 0, because we're looking at the area between 6 and 0, and we divide it by the number of rectangles. Now, the number of rectangles is this number right here, the 3. So that's our width of each rectangle, right? So that's where the 2 times comes from every time. So the way that we can write this then, let's look at this. Oops, no, I put the point on and not the label. Now this looks kind of complicated, right? But this is the way that we represent this. So this is L3. Now this is the way it's supposed to be written. I could finally figured out how to do the subscript for the sum. But this means the sum, remember that's from, this is the heights, f of, right? The heights here. And then delta x is our width of each of our height, or width of each of our rectangles. So we found out in this case, the delta x was 2, so that's, I filled in the 2 over here, right? And so if you think about this f of xi minus 1, so when it's a left endpoint, we put I minus 1, and that's because what I want for my left endpoint is this number here, is the f of 0. So if I plug in 1 into my I minus 1, then I get f of x1 minus 1, which is x sub 0. Now I haven't said that yet, but the way that I label these, this one is like x sub 0, this one would be x sub 1, this would be x sub 2, and this would be x sub 3. Okay, now we're not going to use all 4 of these in this one because we don't use the right endpoint. So we want our first one to be x sub 0, which is this one. I have one later on that's labeled, but this would be my x sub 0. So that's what I want. So that means that's where I have this, right? When I put in x, or n is 1, then I get f of x sub 0, which is this point here. So I end up with my delta x would be 2 times f of 0. So that gives me this one. Now when I plug in n is 2, then I get x sub 1, which is at this place right here. It's kind of like counting. It's sort of like there's 1, there's 2, there's 3. So this is x sub 1 here. And so that gives me this calculation when I plug it in. It would be delta x2 times f of 2, which is this height. And then the last one I plug in, so this is the number of rectangles on top that I'm going to have. So this is my last one that I'm going to put in, is 3. That gives me f of x sub 2 times delta x, and that's this calculation here. So the delta x is 2, and then f of x sub 2, so this is 1, this is 2, that gives me the f of 4. And then this is how we write it. Now, it's really not super important when we're only summing up 3, but I kind of want to get you used to the notation here a little bit. That's what I'm doing. All right, so that one was a little bit more accurate, so let's jump up a little bit. So this time, we will look at an R6. So that means I'm going to draw 6 rectangles in here using the right endpoint of each one as its height, okay? So let's see what this looks like if it's a little bit more accurate. So there's my 6 rectangle widths, and let me draw in and do my shading here. I intentionally didn't allow you to see all my there's a lot of formulas over here which you don't really need to see. Okay, so now I have, again, my delta x here is b minus a over n, right? So in this case, so 6 minus 0 over 6, which means each one has a rectangle of width 1, so that's not difficult. So each one of my areas is just going to be essentially the height times 1, which will just be the height. All right, so, and I'm using right endpoints here. So here is my first right endpoint, right? So I'm going to have, let's see if I can find my labels here. There's my first one, right? So this one has an area of 4.1 because my width is 1. So basically it's just going to be 4.1 times 1, which is this, right? So then let's see, I have my second one is 4.4 because my height up here is 4.4. Really want these. So then the area of my next rectangle then is oops, skipped one, but that one is 5.6 because my y coordinate up here is 5.6. And I have, oops, skipped a, where did my middle one go? Here's 7.6, so that's the bigger rectangle. Did I miss some? Oh, there we go. Okay, so there's that one is 4.4, and then this one here is 6.5, and so my entire area here is the sum of them. So 4.1 plus 4.4 plus 4.9 plus 5.6, and this is equal to 33. Now, this one is, I think, even a little bit more accurate, right? So what was our last right endpoint? That one was 37.5, and we knew that one was way too big. So this one is a little bit more accurate, right? We're starting to like narrow down our window a little bit. Now the way that we write this one with an R with a right-hand sum is this one, if you notice, this is just f of xi because we actually want to start, if these are labeled, this is my x0 here, right? So that's my essentially my endpoint there. This is x sub 1, this is x sub 2, this is x sub 3, this is x sub 4, x sub 5, and x sub 6. Not because they're 6, 0, but because that's my sixth partition, basically, the end of it. So this one gives me, when I plug in 1 first, that's going to give me f of x sub 1, which is this one, right? So that's this calculation here, and delta x is just 1 in this case. So then each one of these, x sub 1 is this height here, x sub 2 is this height, x sub 3 is this height, x sub 4 is this height, x sub 5 is this height, and my last one, 6, is this one here, okay? So I don't use x sub 0. And if you noticed in my left one, I didn't use the right, all the one over here, so that we didn't use 0, 1, 2, 3, x sub 3 over here. So there's always one of these that we don't actually use as the height because we should only have 6 things that we calculate. So there's 1, 2, 3, 4, 5, 6. And so now this we can say is equal to 33. Now let's get a little bit more precise. Notice that every time I kind of go up, my approximation gets a little bit more precise. And so this time I'm going to use an L12. So that means I'm going to use the left-hand part of my rectangle, and I'm going to draw in 12 rectangles this time. Now this time, oops, okay, so I've left on my calculation here already, which I didn't mean to, but this is what we're going to get in the end. So my delta x is b minus a, so 6 over minus 0 over 12 this time. So my delta x here is a half, and since we're using L12, we always use f of x sub I minus 1. And you'll see here in a second where I get all my calculations from. So let's draw in our rectangles. So this time I've got many more rectangles. So this one took a lot of more geometry here. I'm just breaking them up here. So remember, I'm using the left endpoints in every time, so that's kind of why I'm drawing them. So here's my height of my left, right, and there's my rectangle. So again, this is going to be a lower sum, right, because it's below, and I can clearly see that I haven't caught all of the area here. Okay, so there it is, okay? So let's see. So essentially what I did was took a half times each one of these. So f of 0, f of a half, f of 1, f of a half, 1.5, and so forth and so on. And so this gets even better, right? You can see there's a lot less area in here. And so if we kind of look at this, let's see, this one I've got. So let's look here. Why isn't this showing me? So basically you can kind of see here, so this is if I have no rectangles, right? And if I have 1 or 2 rectangles here, there I have 10, that's a little bit better. If I have 30, that's 40 actually, that's a little bit better. And you can see here as I keep going up, so I'm now at 160. If you kind of zoom in, you can kind of see there's little ridges there, but essentially, eventually, as n gets really, really big, essentially my rectangles become just slivers and it looks like my whole area. So this is kind of where we're going with this and how we're going to use this. So let's do one more example. We'll calculate the upper and lower sums. Okay, so now this, I'm actually going to tell you this one. So this is the graph of f of x is equal to x squared. And we are looking at the area under the curve between 1 and 3. Okay, so I thought we would do the upper and lower sums for, we're going to make 4 rectangles, and we will use the right and the left hand approximations. Okay, so I think we'll start out, I don't know, let's start out with figuring out what our, if we're going to make, so now this time I have them labeled. So my left endpoint is x sub 0, and then I'm going to break them into basically 4, so 3 minus 2 over, I'm sorry, 3 minus 1 is 2 divided by 4, so that means each subinterval will be a half. And so each one of these, so my x sub 1, or x sub 0 is 1, x sub 1 is 1.5, x sub 2 is 2, x sub 3 is 2.5, and x sub 4 is 3. So my x sub 0 is my left endpoint. My last one, you know, if I'm doing L4 or R4, then my last one will be x sub 4. All right, so let me put in my things here. Oops, that's not what I wanted to do here, sorry. Okay, so let's, all right, let's put on our rectangles here. So, all right, now this time I didn't draw the parallel to the x-axis ones, okay? So this time, so if I want to do L4, so I'm gonna have my area of each one will be 1/2 times, and then my L4 basically means I'm going to go to, so my L4 means I'm going to use x sub 0, right, as my first height, so my first rectangle would run right across here, right, so I'm going to have, this will be a lower sum, I can kind of tell already. So then my next rectangle, this is its height, and I would run it, actually it's 2.25, and it's going to run straight across here until I hit this one. And my next L height will be at 2, so that'll be 4 times 1/2. And then this one here will be at f of 2.5, which is 6.25. And so basically each one of these, so I'm going to have 1 times 1/2, 2.25 times 1/2, 4 times 1/2, and 6.25 times 1/2. That's going to give me my approximation for L4. Okay, so I have it written here as all nice. So I have the half factored out because we can multiply each one of these ones by 1/2, or we could just factor out the half. So I just added them up together. So I add f of 1, right? So that's this one. That's x sub 0, f of 1.5, f of 2, and f of 2.5. Those are my 4 heights. And then I have, each one has a width of 1/2. So when I multiply it by 1/2, it's like I can distribute this whole thing, and I'm going to get 6.75. So this is going to be my lower sum. I can tell because when I draw these, you know, like sort of imaginary things right straight across here, like I can see that I'm still going to have shaded area up above that I'm not going to catch. So my R4 must be my upper sum. Now again, remember, earlier I caught there was a mistake that I didn't point out, but I had the 2 sums up and one had a different number at the top. They should be the same. So this is the number of rectangles. So since I'm doing L4 here, I go from n is 1 to 4, and then basically this means when I plug in 1 here, that means I'll have x sub 0 will be my first one. So that means I'm going to use this one. Okay, so now when I use my right endpoints, I'm not going to use x sub 0. Remember, my R4, actually, I don't use the I minus 1, I just use f of x sub I. So my first one will be x sub 1. So when I use my right endpoint, so here's my first rectangle, that means I'm going to use this height as my rectangle, right? So this is going to be my upper sum because if I draw this line parallel over here, I'm definitely going to have more area than is necessary. And then I'm also going to have this one, right? So this first rectangle will be 2.25 times a half. This next one will be 4 times a half. This next one will be 6.25 times a half. And this last one will be up here at 9 times a half, right? So essentially what's going to happen is I swap out this f of 1 for f of 3. So I only ever use one endpoint. So if I'm going to use my left endpoints, I'm going to use obviously the left one and not the right. And if I'm going to use my right endpoints, I'm going to use the right one and not the first one. So the way that I write this one here is like this. So this is my R4, okay? So this 5 here is actually just a thing on the y-axis, so that has nothing to do with it. Let me actually, can I move this? There, we'll move it down a little bit more here, okay. So this one is R4, they're almost identical because they both have n as 1 to 4. This one, the only difference is I'm going to start with I minus 1 as my first subrectangle. So this one I'm going to use when I plug in 1 first. I get x sub 1. That's going to be my first height. So essentially, I'm going to this sum up, and I end up with, when I multiply by a half, of 10.75. Right? This definitely one should be bigger because these are going to, I'm definitely making a bigger rectangle. Like here is definitely over an approximation. Now, of course, the more and more rectangles that I make, the more accurate that my thing will be. But in the end, I know for sure that the real area, I might not be able to pinpoint it right this moment, is somewhere between 6.75 square units and 10.75 square units. So we're narrowing it down. And the bigger that my number of rectangles that I use, the less error we're going to have. And so that's, maybe you can kind of see the writing on the wall, but we're going to take essentially the limit as we put in n rectangles and make it fit just perfectly. So we get that picture of the nice smooth curve. And so that's where we're going.